continuar.
Hey, let me set the plot for you. You have an application which is in production doing quite well, and suddenly your users started requesting a feature to allow them to search for content on your system. Being the core developer, it is then up to you to find a solution. You open up your favorite search engine to find the one, and Algolia is the top result. It seems great and all, though there's a catch: vendor lock-in, which immediately terrifies you. You then discover Elasticsearch, an open source solution which perfectly fits your use case. Though you can run it on your own hardware, you decide to have your Elasticsearch servers running on AWS with the following architecture. After deployment, the users are happy and management is smiling. But wait, your spider sense is tingling. As a proficient developer, you realize that this approach is not secure. Elasticsearch is exposed to the internet and anyone can literally access or modify the precious data. You then place Elasticsearch in a virtual private cloud, which essentially hides your servers from the world. This is good and all, but unfortunately, it's too secure in that our users can no longer access the content in Elasticsearch. To allow access and maintain the good security, we introduce a Lambda function which will talk to Elasticsearch on behalf of our users and any of our company systems which want to access it. And finally, to access Kibana, we'll create an SSH tunnel between our machine and an EC2 instance, which is running in the same VPC as Elasticsearch. EC2 is just a fancy word for a virtual machine. All these steps are time consuming, but luckily this is not 2010. Terraform allows us to describe an infrastructure in a text file and then create it for us without having to click through multiple menus. Enough with the rambling, let's get going. On your AWS console, head over to the IAM dashboard and add a user. Make sure programmatic access is checked and download the CSV file. Go to terraform.io and follow the instructions of your platform to install it. Clone the GitHub repository in the description. In the terraform.tf file, set the access key and secret key to that of the CSV file recently downloaded. The EC2 AMI refers to a virtual machine identifier. If you want to change it, go to the EC2 dashboard and attempt to launch an instance. Next to the OS name is the AMI. While we're here, we may as well create a new key pair. I'll call mine my key pair. Move it to the SSH folder and modify the permissions. We'll make use of this file later on. Open the terminal and initialize Terraform by running Terraform init, and then do Terraform plan to see what changes Terraform will make. Run Terraform apply and watch as the magic unfolds. Next, visit the Elasticsearch dashboard and create a new domain. Make sure production is selected since that's what we are using it for. Since I don't have the big bugs, I'll choose the small instance types. Select the production VPC and the subnets created by Terraform. To allow all that's on our subnet to send requests to Elasticsearch, we'll set the access policy to open. Review the configuration and confirm once done. While Amazon sets up our Elasticsearch servers, let's create the Lambda function. Clone the second GitHub repository in the description. Install pipenv for the virtual environment. In the virtual environment, do a pip install from the requirements file. Zapper will allow us to deploy a Flask application as a Lambda function. For security, we'll create a group meant for Zapper and add our own inline policy. Replace my account ID with your own. Go to Users and add one which will be used by Zapper. Make sure you select the group we just created and download the CSV file. Finally, create the credentials file. In the virtual environment from before, run Zapper init. A settings file is created to which I'll add a couple attributes to suit my need. In the Flask app, adjust the variables to your equivalent. As for our endpoint, all we do is accept a query parameter and then send it through to Elasticsearch. We are not sanitizing it now, though you could do that. I would recommend you do that. That's it. The API is now ready for deployment. Our API is now up but cannot access Elasticsearch since it's not in the same VPC. Let's fix that by going to the Lambda function and set the VPC to that with Elasticsearch. Confirm it's accessible by doing a sample query. Now, for the sake of preventing just anyone out there from calling our function, we'll restrict access by requiring an API key. This measure will be enforced by the API gateway. Create a usage plan and set the throttling to your liking. In my case, I'll disable it. Associate the API with this usage plan. Next, create an API key for the plan. Now let's make sure that all requests to this API require an API key. Redeploy the API and try sending a request again. Awesome, request is denied. You place the API key in the request header for it to actually work. That should mostly be it all. But then if you wanna access Kibana, then you may wanna watch further on. The final step is to set up an SSH tunnel. In the SSH folder, create a config file and set the values accordingly. Hostname is the public IP of the EC2 instance. Identity file is a path to the downloaded key pair file. Set local forward to the Elasticsearch address. Start the tunnel and try accessing Kibana. Voila, it works. Let's use Kibana to write some data. We can then query this data through our API. Perfect, we have successfully deployed our Elasticsearch servers. In a later video, we'll hook up Firestore with Elasticsearch, such that any new data which is in Firestore also gets reflected in Elasticsearch. And also if it's updated or deleted, the same happens on Elasticsearch. Let me hear what you thought about the video and also how I could improve making these videos. Otherwise, until then.